Good to go.
Awesome.
Awesome. Cool. We're very happy today to have Nick Rod with us, telling us something about dark matter.
Thank you. Yeah, it's very nice to be here. Thank you all for the opportunity to come and visit. I have to be honest, there's an extra reason it's very nice to be here. I'd already planned this trip to Chicago for another conference and then the government shut down. So the fact that I'm visiting here, it means that I can get some reimbursement. So but also I'm very excited to be able to share some of the science I've been thinking about recently. And the focus of the talk today is to share with you where I am most optimistic about a discovery of dark matter in the next 10 years. And this reason for this optimism comes from this instrument called the Cherenkov Telescope Array Observatory, or CTAO. And one of the aspects of this instrument that I like the most is that I don't need to show you an artist's rendition of what this telescope looks like. As far as I'm aware, this is not an AI-generated image. It's a genuine image of the first of the telescopes that will form a suite of instruments that come together to be CTAO. And it's already operating, and it has already collected data such that they should have their first searches for dark matter coming out any day now. But it's something that is going to become more and more powerful over the next decade. And I want to share with you why I have genuine optimism that this is the instrument that could discover dark matter. Okay, so that's the basic idea I want to share with you, but let me run through how I'm going to organize my time today. Firstly, to be upfront, the types of models that CTAO can search for primarily are TeV scale thermal WIMPs. Now, if I was giving this talk 20 years ago, we would just skip straight through the motivation. But of course, these days, the thermal WIMP is maybe not everyone's favorite model of dark matter anymore. So I'll just give you, maybe a bit of a pep talk for the WIMP and explain why you should still have some optimism that this could be the dark matter of the universe, and therefore an instrument that could reach its target sensitivity could really make a discovery. After that, I'll tell you about my favorite way of searching for these WIMPs. This is this idea of indirect detection, and I'll explain to you all of the ingredients one needs in order to make a robust prediction for what CTAO should see, or how we should interpret the results if CTAO is unable to actually see a signal. And then finally, I'll tell you about what you can do with this instrument here. Okay, and to state the obvious, please interrupt me if you have questions at any time. I'd be very happy to hear that. So let me start out by just running through the motivations for the types of dark matter candidates that CTAO might be able to detect. So of course, in many realizations of where the WIMP was the dark matter of the universe, we would have seen something in other experiments already. Of course, that's a given. Nonetheless, I think it's a true statement that the WIMP is a very deeply motivated version of what dark matter could be. The fact that something around the TeV scale with an electroweak strength interaction naturally gives you the right relic abundance, I still think is very compelling. And the other aspect of this, especially as is relevant for indirect detection, is that these sorts of scenarios remain deeply discoverable. The same interactions that set the relic abundance in the early universe predict that these dark matter states should be annihilating today in a manner that we could detect, as I'll tell you about today. So the fact that these things are discoverable, I find very nice. So there are various ways of motivating these types of states. Maybe the idea that has been a bit more in vogue in the last 5 to 10 years is to think about model building from the bottom up. And the perspective here is that you take the standard model as we know and love it, and then you try and ask, what states could I add to the standard model, just sort of a single state, that would explain everything that we know about dark matter? And this is really the spirit of this beautiful paper that actually is now 20 years old, called Minimal Dark Matter by Marco Torelli and others. And what they thought about is what are the single representations that you can add to the standard model that would explain what we see about dark matter. So there's various realizations of this, just to pick one. For example, you could add a 5 of SU2 to the standard model, but make it neutral under hypercharge. And then after electroweak symmetry breaking, these 5 Majorana fermions will rearrange themselves into a doubly charged and a singly charged Dirac fermion, and then you'll have a neutral Majorana fermion that's left. And one very nice thing about these models is that after electroweak symmetry breaking, there's some energy associated with having charge. So generically, even though all of these states will be degenerate in the UV, after electroweak symmetry breaking, the neutral dark matter will be the lightest state you're having in this state. So then in these models, because they're just interacting through the standard model interactions, there's no freedom to tune the interaction strengths. They're already fixed by what we've measured in an experiment. The sort of one new free parameter you have once you've added this multiplet in is what is the mass of these states. And then the mass is fixed by just getting the right relic abundance. And so for the quintuplet, you can find out that the correct mass, if you want to explain the relic abundance, is about 14 TeV, okay? So then in this sense, these are then extremely predictive scenarios. You've added, you know exactly what the interaction strength is and you know what all the parameters of the theory are. It's just a question of sitting down and computing, is this model already excluded or what would you need to do to test it? So this is one realization of these types of models. But of course, the hope is that by finding dark matter, of course, that would be fantastic, but also we might learn something about the UV. And so it's very reasonable to ask, is there similar ways of realizing these ideas from the UV? And the truth is there generally is. The idea here would be, of course, in the UV, you don't just add one state, you have some spectrum of additional particles. But at low energies, you better get the standard model, of course. And then hopefully you would also get some dark matter candidate coming out, plus some other things that maybe you imagine are quite a bit heavier. And so, for example, in the context of supersymmetry, this can be realized and give you these famous neutralinos, simple examples of which would be, say, the WINO or the higgsino, the partners of the W bosons and the Higgs. And of course, actually, even though these come from specific UV motivations, you can also think about these as other examples of minimal dark matter. These are just simple representations of the standard model I could have added in. And if I ran through the same calculation, I find the higgsino has a mass of about 1 TeV and the WINO has a mass of about 3 TeV, for example. But as far as supersymmetry is concerned, you're not going to realize, as far as I'm aware, anything like a 7 of SU2, for example. You usually realize these minimal representations. However, there has been work on realizing that you can actually come up with scenarios where, for example, you have some confining dark sector and the dark matter itself can actually behave like it's charged under one of these higher representations. And Puya's done some very interesting work on that as well. So there can also be UV realizations of those scenarios too. So that's just a sense for the type of models you're looking for. And as I said, the point I really wanted to emphasize is that in these scenarios, essentially everything is fixed. Of course, there's caveats to that, but they're extremely predictive. So now it's really a question of sitting down and doing the calculations and finding, are these models already excluded or are they potentially in reach of the next generation instruments? So this is a huge program that people have been thinking about extensively. And of course, one of the classic ways we have of looking for dark matter is direct detection. And I'm showing you what the projections for these various models are for direct detection on this slide here. So this is some beautiful work that was done by Salvatore Bottaro and collaborators. It's actually 2 different papers, but they both came out in 2022. And what I'm showing you here on the left-hand side is what is the predicted cross-section for direct detection as a function of mass for these real representations. These are all the minimal dark matter candidates that don't have any hypercharge. And the WINO is one example here. And on the right-hand side, I'm showing you the complex representations, which includes the higgsino, for example. So one thing to note is that even in this plot, it's already somewhat out of date. It's not that old, these papers. But actually, you can see there are these LZ projections here, or I prefer LZ. And what you would actually find is that these projections have now been achieved. So actually, this parameter space here is already essentially excluded. Nonetheless, in these models, none of them live between LZ and where Panda X would have seen. So you wouldn't have expected to see anything yet. And in fact, most of the models live between where LZ is now and where essentially we would have to get to with some future instrument like XLZD to get down to the neutrino form. Of course, there's actually a counterexample to that. Not all of them would be reached. And the famous instance of this is the higgsino. When you sit down and actually do the calculation, there's an accidental cancellation, as far as we can tell, for a 125 GeV Higgs. That means that the higgsino cross-section is extremely small and is deeply into the neutrino floor. So even with a future instrument like XLZD, you have no guarantee you'd ever see the higgsino if that is the dark matter of the universe. But for many of these other candidates, they are alive and kicking from the perspective of direct detection, but within reach. Okay. The other way we have of looking for WIMPs is, of course, the prospect of searching for them at colliders. So there's a bit of a lag here. Okay, there we go. But as I mentioned to you earlier, the WINO has a mass of about 3 TeV, whereas the higgsino has a mass of 1 TeV. And one can just sit down and compute, would you be able to search for this at a collider? There's many different ways you can look for this. For example, one of the classic ways is you could produce one of the charge states in the spectrum, and then when that decayed down to the lighter neutral state, you would have a charge track that essentially would vanish, so there's some disappearing track. And it turns out it's just much harder to look for the higgsino than the WINO in this case, because the track is a factor of a few smaller. So I think one of the classic papers that studied the reach of for these models at future colliders was by Matt Lowe and Leanne Tao about 10 years ago. But a more recent update showed that these models at their thermal masses seem to be out of reach even for high LUMI LHC, but they probably would be in reach of FCCHH if that ever gets built. And I mean, probably this sensitivity will be reached after I leave this Earth. So that's a bit disappointing, but at least they are in principle, these are instruments that you could reach at a future collider, okay? But we wouldn't have seen anything just yet. So that is just to say that we know of three basic ways of looking for these minimal dark matter scenarios, or these minimal realizations of the thermal WIMP. And in most of the cases, you never would have seen anything yet at direct detection or colliders, although in many cases in the far future it's possible that we could see a reach of this. Of course, where I'm going with the talk today is I want to emphasize, what I want to explain to you is that this other way we have of searching for thermal WIMPs, this technique of indirect detection, has a very high chance of actually seeing a signal in the next 10 years, even though we wouldn't have seen anything at these other instruments so far. Okay, so if you've ever worked on indirect detection before, you would have seen this expression I'm showing you here many times. If you haven't, that's okay. The purpose of the next 20 or 30 minutes is to carefully walk through what's happening here. So the idea is, if the dark matter of our universe is a higgsino or this quintuplet, then there'll be a large overdensity of this dark matter towards the galactic center. And occasionally these particles, they're Majorana fermions, so they're their own antiparticle. Occasionally they'll meet each other and then they can annihilate into states like photons that we can try and see at our detector. So what one wants to do in order to know if you have any hope of ever seeing this is to sit down and compute what is the flux of, say, photons you get from this process, say differential in energy. So you know how many is a function of energy you would get out. So this famously depends on two different factors. The first factor I'm showing you here controls when these two particles come near each other, what is the probability they undergo this annihilation process, and then what is the distribution of states I get out of this annihilation. So I might ask about the distribution of photons or anti-helium-3, for example. But ultimately, what I need to know is this is just some field theory calculation where I take two incident dark matter particles and I ask for the probability of getting a photon at some energy coming out the other end, okay? So this, you might think, for these models I've told you about, would be essentially a first course in field theory homework problem. I said to you, all of the parameters in these theories are fixed. So we just have to sit down and just compute what is the probability that they annihilate and the spectrum that comes out. It turns out that this was not something you could have just done in your first field theory course. And to give you a flavor of how involved this is, I'm showing you here this cross-section, or this probability to annihilate for one of these specific models that I told you about earlier, the quintuplet. And I'm showing you what that cross-section looks like as a function if I change the mass of the quintuplet. And if you've ever done a simple tree-level field theory calculation, when you plot the result, it generally doesn't look as involved as what I'm showing you here, okay? So this is just giving you a hint that there's actually a lot of richness in these models. Even though everything is predictive, there's quite a bit to go in and capture what's going on. So let me just describe to you some of the key features here. So firstly, you can see these enormous spikes as you move along as a function of mass. Where are these coming from? It turns out that these are essentially due to a non-perturbative effect called Sommerfeld enhancement, which, if you haven't heard about it before, that might sound like fancy words. But really all this is saying is that if you're computing the probability of something annihilate, if these states have some attractive interaction between them, you can have an enhanced probability of them annihilating. So of course, because it's got the name Sommerfeld, you can guess this is a very old phenomenon. It was known back to the 1930s. And it's essentially saying that an electron and a positron, if you include their charges, will annihilate more often because they're sort of pulled towards each other. However, as we moved into doing field theory calculations at the tree level, tree level effects don't capture this sort of physics. So for a long time in the world of dark matter, people had just forgotten that you need to include these sorts of effects. And then eventually it was realized you could put them back in.
Yes.
Please.
The pattern of peaks and their distribution and how much they go up and down, like, seems a little bit more, it's not as uniform as, for instance, a triplet case. Like, are those just numerical artifacts, or there's just some deep thing about quintuplet?
No, okay. So that's a very good question. Let me just briefly explain for just so everyone's on the same page where these are coming from, then I'll explain to you where this richness is coming from. And actually we'll see it is there is a special feature towards your question about this being the quintuplet as opposed to just being the WINO, for example, where you just have the singly charged state here. And later on, I'll show you what this looks like for the 13, and you'll see that the richness only grows. So yeah, just to explain where these peaks are coming from. So it's not that as the two dark matter particles come towards each other, they're neutral. So this idea of the electron and the positron can't be a direct analogy. However, the distance scale over which they have to come within each other for an annihilation will be of order 1 over their mass, okay? Because the generic scale you'd expect for the cross section would be 1 over the dark matter mass squared. So the statement is that you need them to get of order 1 over the dark matter mass for them to annihilate, but well before they get there, they will come within 1 over mw. And because these states are charged under the electroweak symmetry, at that stage they can exchange a W boson, for example. And because you have these charged states in the spectrum, once you've exchanged a W boson, you can now have the chi plus and chi minus, which can have an enormously enhanced cross-section of covering that final bit of distance between 1 over mw and 1 over m chi. Now, that all sounds reasonably straightforward, but then of course, when you sit down and do the calculation, it turns out that there's quite a bit going on here. Like, why exactly do you get this spectrum of this structure of peaks? Actually, what happens is when you compute this process, you find that due to this potential that these particles experience, you can have a spectrum of bound states that can be created when these particles come near each other. And as you change one of the parameters of the model, the mass, you'll change the binding energies of the number of bound states you have and the binding energies of the bound states in the spectrum. Occasionally, you can have a bound state with a very, very small binding energy. And so that means when you have these particles coming in very slowly, because dark matter in the galactic center is moving at only 1 part in 10 to the 3 of the speed of light, you can effectively produce one of these bound states almost on shell, and you get an enormous enhancement to the annihilation cross-section, okay? So this is something you just have to do a detailed numerical calculation to get out, but that's the intuition for what's going on here. Now, coming back to Puya's question about why there's this enhanced richness once you go to these higher states, I mean, the glib answer is you just have more states that you can exchange into. The spectrum of bound states is just much more complicated. But actually, more to the point, once you have these additional states, you actually have multiple attractive eigenvalues in the potential matrix that you're solving. Compared to with the WINO, you have a single attractive eigenvalue. And so now you can actually have interference between these. Sometimes one is dominating compared to the others. And we'll actually see an additional effect associated with this point in a slide or two. Okay. So that's just saying the cross section. And one other point so I spent all this time talking about the Sommerfeld enhancement. One other point that I spent several years of my life working on, so maybe I'll say a few words on it, is the fact that you might notice that what's being plotted here, there's this technical term next to leading log accuracy. So if you don't include this Sommerfeld enhancement, you get the answer wrong by many orders of magnitude. So you probably want to include that. But another effect that you can wonder here is that the dark matter mass, I said, is at 14 TeV, and there's this other state in the spectrum, the W boson, which is at about 100 GeV. So as soon as you start computing this, I think there was a paper back in 2010 or so, which did the one-loop calculation version of this problem, and they found that it was a huge correction to the tree level process. And the reason, of course, was that there were large logs around of order the dark matter mass over the W mass. But if you team up with collider effective field theorists, they know how you can actually do these calculations in detail, and we did exactly that. And for the quintuplet, this was some work that we had published last year. We were able to resum all of these effects such that you get down to order percent errors. The error band is what you can show here when they're included. And if you leave this out, you can easily get the answer wrong by a factor of 5 to 10. So it's important, but we know how to include this. Okay, so that's the probability for two particles to annihilate when they come near each other. The other question that the particle physicist can answer for you is what is the distribution, the particle physicist being me, of course, but what is the distribution of states that come out of the annihilation? So the dominant one that people normally focus on is the 2-photon final state. Now, that might initially seem surprising. We have neutral dark matter, and I'm telling you, I'm looking for its coupling to 2 photons. At tree level, that should be 0. And indeed, that's correct. It's only at loop level you get this. However, if you had chi plus, chi minus, they have a tree level annihilation to photons. And through this Sommerfeld process I told you about, it's just as likely, well, you can be much more quantitative, but it's certainly not improbable that at the end of this process of exchanging W bosons, you end up in a charged state as opposed to in the neutral state. So it's very plausible that you have, well, you can just compute it. You get a large annihilation cross-section to this 2-photon final state. And because, as I said, the dark matter is roughly at rest in our rest frame, the photons that will come out will be essentially a delta function at the mass of the dark matter. And then when you go to a real instrument, a delta function gets smoothed out to some Gaussian due to finite energy resolution. But this is the smoking gun signature you'd be looking for in these scenarios. Of course, in some models, you'll only see a continuum, and it's still possible you could detect that. But this is the sort of effect that, as far as I'm aware, we have no idea how to astrophysically generate order 10 to 20 TeV lines of photons, okay? At lower energies, there's many processes that generate lines of photons, but not at these energies. So this would be sort of the smoking gun. So again, this is what people knew about for a long time, but once more, the physics of this is much richer than what was originally expected. A secondary contribution you can have in these cases is that beyond just having 2-photon final state, you can have, generically, you can have a 1-photon final state plus other radiation, which is, as long as it's sufficiently collinear, this photon will be almost at the energy of the dark matter mass. And so if you ask, what is the collection of all processes where I have a photon back reacting against collinear radiation, essentially you're asking for the cross-section to produce a photon plus a jet. And so again, luckily we teamed up with collider effective field theorist experts, and so we're able to compute the corrections you get when you add in this photon plus jet process, where this is an electroweak jet. And it turns out that this gives roughly a factor of 2 enhancement to what you see at the line, if you hadn't included that. And that factor of 2 was a lot of work, but we've now included it, and it only boosts the possibility of seeing a signal. So the last contribution that you can have to this is the so-called continuum contribution. And so where this can come from is, just as you could annihilate to photons, well, surely you could also annihilate to Z bosons, or similarly for other, you could also have WW in the final state. And in that case, those states will decay, those decay products will shower and hadronize, mostly produce neutral pions, which when they decay will give you lower energy photons. So you just get some lower energy tail contribution, which can be important, but generically it's harder to look for because it'll look somewhat degenerate with many of the backgrounds that you have, whereas the line is really the unique shape. The other contribution here that can sometimes be very important is that I told you earlier on that you can form bound states through the annihilation. Generically, these bound states, when they decay, will give you lower energy photons as well. So you have to include that too. Okay, so that's just telling you the various ingredients that go into this, but let me point out one aspect of this calculation that we found for the quintuplet that I'd never seen elsewhere in the indirect detection literature, which actually builds on the question that Puya was asking earlier on. So of course, again, these models are predictive. We know roughly what the mass should be, but you can ask, as you change your one free parameter, the mass, how does the spectrum vary? And what I'm showing you here is what the spectrum looks like for roughly the thermal mass at 14 TeV. Then if I increase the mass to 16 TeV, which is not that much higher, you see the spectrum goes up to what I'm showing you here in dash green, whereas I now go a little bit higher in mass, the spectrum plummets down to 18 TeV. Sorry, down to this result here I have for 18 TeV. So why is this happening? The reason is that there are these different contributions to the spectrum that I mentioned to you, and each of them are dependent upon the probability of ending up in various final states at the end of this Sommerfeld process. And as I said to Puya, once you go, just to emphasize, this doesn't happen for the Wiener, for example, but once you go to the quintuplet and you have multiple attractive eigenvalues in your potential, you can find that you sort of have a different set of Sommerfeld peaks for each of these. And maybe one process is being dominated by one Sommerfeld peak, and at one point you can be falling off one, but the other one can be start to building up. And so you can get very rapid changes in the shape of the spectrum as a function of mass, which is not something I've ever seen in indirect detection before. Broadly, just the spectrum changes relatively smoothly as you change the mass, but here it can change very dramatically.
Wait, does this also happen with like larger represent? I would expect this also happens with even larger.
It gets, yeah, it becomes more and more dramatic, exactly. And I'll give you, in our paper, we have what this looks like for the 13, and you see this is very dramatic, but already to give you a hint of the drama, here is what the direct cross section looks like for the 13. So remember, Puya was saying like, what's all this structure for the 5? Yeah, but then you can see.
So eventually, if you go to infinity, probably I should assume essentially a uniform distribution.
Sure, but then you'll have another problem before you hit infinity. So for the 13, just to emphasize, you now have a state with +6 charge in the spectrum, so it's pretty crazy. But of course, already the 13 is a bit unpalatable, because if you're adding in these states with enormous charge under SU2, you'll be pulling down the Landau pole of SU2. And I can tell you for the 13, the Landau pole is like a factor of 2 away from the mass. And if you went to the 15, for example, the theory just doesn't make sense anymore.
But there is also another thing. I mean, you see the peaks. One way you can think about it is that the bound state has overlap with, like, you have chi-naught, chi-naught, and chi plus, chi minus in the eigenvalue, the eigenvector. But eventually, I expect if the mass, the charge goes really high, the overlap between the neutral state and something that is made of chi plus 10 and chi minus 10 would be very small. And so is it, so I guess I'm getting at if actually the charge, the largest charge, keep getting larger and larger, it's not like that you keep getting more and more complicated spectrum just because overlap with larger charges become small. Incoming is
yeah. So, look, just to be honest, the way that these things are done, you set them up as a detailed numerical calculation and you get them out. So all I can give to you is the words I have to stomach the answer that comes out of that. But the truth is, the way I think about this is that by the time you have the 13, you just have many, many more bound states that are possible, right? Because in these things, you can often even form charged bound states. That live like a +2 couples to a -1, and then that can form some. And really what matters for the Sommerfeld, these peaks, is there a state with a very small binding energy? And just by having many, many more bound states, the probability that there is one that has lower binding energy is increased. But that's just, I mean, these are just some words that I put on at the end of the detailed numerical calculation. It's a fair point, but it does sort of bear out in detail that we see this greater richness. There's one other aspect of the 13 that I wanted to emphasize, is I told you that in these scenarios, you can be really predictive about everything that's going on by you just fixing the mass, for example, by getting the right thermal relic cross-section. You can see that this is starting to fail a little bit by the time you get to the 13. You can see that we have a central prediction for the mass of about 300 TeV, but actually there's a huge range around this where that could be. It turns out that the reason for this is that you know for the 13, essentially because it has this enormous charge, that if you go and compute the potential that gives rise to these Sommerfeld effects, you can guess that the one loop corrections to that potential will be enormous because you can have these hugely charged states in the loop, but no one has carefully sat down and worked out all of these higher order corrections. So just by estimating the size of the error on these potentials, you get this huge uncertainty band. I'm told this was actually the size of this uncertainty band was in some work done by Diego Redigolo and Salvatore Bottaro, separate to us. We just used it in our paper here. But you could, with enough work, massively reduce that uncertainty band. But at the moment, we have to just admit we're not quite sure where in this range the thermal mass is. So you have to exclude all possibilities of this if you really want to say that this is not the dark matter of the universe. And again, that's something with more work one could do, improve on in the future. Okay, so just to sum up this first part of the indirect detection flux, I would say that hopefully you've gotten an appreciation that actually the physics of these models, even though everything is sort of predictive, is much richer than maybe you would have naively expected. And I think what the field is richer than the field appreciated roughly 20 years ago. But broadly, with sufficient work, we're confident that in all the models we care about, you could really pin down the uncertainties on this factor here to order 10%, okay? So for many models, this has already been done. For the WINO, there's been some work on the higgsino, but there's a number of other sorts of minimal dark matter candidates where this calculation just hasn't been done yet. But I think at this stage, we have all the tools in place, and I'm confident that in the next 5 years or so, we'll get all the models people care about here, we'll get all the particle physics uncertainties under control, where you're not worried you've missed some order of magnitude contribution anymore. Okay, so that's the optimistic side of the indirect detection flux. Let me turn now to the pessimistic side of the indirect detection flux. So the other contribution you have here is, the first part was just what's the probability of annihilation when two particles come near each other? But to know, there has to be some knowledge about what is the distribution of those particles to know how often they even come in the vicinity to have a chance of annihilating. And so that's what's controlled in this astrophysics part, or this so-called J factor. And what this says is you need to know the detailed distribution of the particles throughout the universe, because when I point my telescope at some a location in the sky, what I'm actually going to see is essentially an integrated column density of the dark matter density squared. Because I need two particles to find each other, that's why I have the square in there. So fundamentally, to make a prediction for what I should see, I need to know where the dark matter in the universe is. And this, you can imagine, is something that I'm not going to be able to pin down to 10% accuracy. But I'll tell you how well we can do it at the moment. Okay, so the sort of benchmark that the community has taken for a long time here is just to look at what is the distribution of dark matter we get out of, say, cold dark matter only n-body simulations. And one of the classical results is that these are reasonably well fit by something called an Inasto profile. I don't know why, but somebody once asked me, is Inasto a person? The answer is yes, it is a person, okay? But it's also a profile of this dark matter distribution, which is more relevant to the talk. So what I'm showing you here is what is the distribution of dark matter. So this is measured in units of GeV per centimeter cubed, which is some hideous mix of units that we tend to use in this. And what I'm showing on the x-axis is what is the distance from the galactic center. Of course, more generally, you could ask about what is the full distribution of dark matter throughout the universe. But as I said, our best hope turns out to be looking for dark matter annihilations in the galactic center. So I'm going to focus on what's the probability of annihilation in the galactic center. So we live at around 8 kiloparsecs from the galactic center. And the question is, we assume the baryonic density goes up as we look towards the galactic center. The dark matter density is presumably doing the same. But the question is, how much is it going up? Because that is really what's going to weigh in on this. So this is what you get from the Inasto profile, but you should already be a bit nervous about the words I said, because this is shown to be a reasonably good fit to dark matter only n-body simulations. And we know that towards the galactic center, there's way more baryons than dark matter, so surely you might be missing something by leaving them out. So what you might worry about is that this is overly optimistic. If you put in too large a value here, you might, if you see nothing, you might conclude, well, the WIMP or the higgsino is not the dark matter of the universe, but actually it just turned out you used the wrong model for the dark matter profile. And if you use the correct one and looked a little longer, you might have actually seen a signal, for example. So that's sort of what you're worried about in the back of your mind. So with that concern laid out, what people have traditionally done in the literature was very crude, but I'm guilty of doing this many times, is you take this dark matter distribution and you just assume that there's some very ad hoc coring at some point. This is what you're nervous about, is that this stops growing at some scale. And there's some weak evidence based on some studies of the galactic bulge that if you had a core that's larger than about 2 kiloparsecs, it probably would be inconsistent with the data. But I think it was very loose. Okay, this is roughly what people had thought. It already seems like a very extreme distribution, so it seems somewhat conservative, but there wasn't a lot of foundation that you could say that this was a really robust lower bound on what the dark matter density could be. Nevertheless, this 2 kiloparsec core you'll see in a lot of papers. They take that as sort of the conservative lower bound, like maybe being extremely conservative. I know people take other values as well, but what the dark matter density could be. What has happened in the last 10 years, however, is that the people running these amazing n-body simulations have started to add baryons into these. And not only have they added baryons, they can do that and get galaxies that look somewhat like the Milky Way. And so we're now in an era where you can take the n-body simulations with baryons and you can ask what happens to the dark matter distribution that you extract from them, okay? So it turns out that it can go in either direction, which I found a bit shocking when I learned about this. Because what you can find, for example, I'm just showing you 2 instances that comes from this Fire 2 simulation. This is the feedback in realistic environment suite. There are multiple other ones as well. Did you have a question, Nico?
Yeah, like how do you find, looks like the Milky Way?
That's a dark arc, yeah. So I think the dominant characteristic that they look for in a galaxy like the Milky Way is it has a similar mass to the Milky Way, okay? They generally also look for it to be a spiral galaxy. But often when you go and just tell you the truth, like we have made, I try and be honest, where we've made enormous strides with these in here. They do get things that look somewhat like the Milky Way, but often when you go and look at something like this one, maybe that could be the Milky Way, I don't know. But when you look at some of the other ones, they don't look anything like the Milky Way. Like they might be extremely disturbed, but they still have the like perturbed. It's not just a simple spiral. Nevertheless, they have many of the other properties like star formation rate and total mass. The experts on this tell me make them plausible dark matter candidates, Milky Way candidates. But of course, there are other factors, like as we're learning more and more, like the uniqueness of the Milky Way, like the presence of Andromeda nearby can have a large impact on this. The presence of the Magellanic Clouds can have an impact. And not all of these Milky Way-like galaxies will have all of those features, for instance. So there's work to be done, but yeah, this is where they're getting. But independent of the work to be done, one thing I want to emphasize, just by taking fire and looking at Milky Way-like galaxies with all the caveats that I just mentioned, you can find that you either get less or more dark matter density than what you got from iron asteroid. So I think the less, I don't know, maybe I'm just projecting my own biases onto you, but I think that the less makes a lot of sense. This is what I expected initially. The less you get, because what you were missing by ignoring baryons was all the supernova that would go off from the baryons in the galactic center. Supernova blow out baryonic gas. And if you had some dark matter particles that was on some orbit, and suddenly there's less mass enclosed within it, it's essentially, it'll evaporate out to a larger radius until its speed matches the gravitational pull within it. And so this is exactly what you see when you have a lot of baryonic feedback. They generically find that you core out the dark matter profile because it's dragged out with the baryons being blown out, and you find examples where it's quite a bit less than iron asteroid. So then what on earth is happening in these scenarios where you actually have an enhancement by the addition of baryons? So although this was a surprise to me, it was not a surprise to astrophysicists. This effect was known since 1986, and it's an idea called adiabatic contraction. And so just to explain what this is, because I think the physics is very beautiful. So again, in our understanding of structure formation in the universe, we know that the dark matter halo formed, the baryons then fell onto this and eventually formed the galaxy, okay? So you can imagine, just imagine some dark matter particle near the galactic center before the baryons are there, it's on its orbit. And what it will see is slowly the mass within its orbit is going up because the baryons are slowly accreting onto this. And sort of by the converse of the argument I gave previously, you can show if this process happens slowly enough, the orbit of that particle will just slowly be pulled in until its rotational velocity matches again the gravitational pull that's within that. And sort of there's an analog here you can think about, like what would happen if you very slowly increase the mass of the Earth, mass of the sun. You can actually show that the Earth's orbit will be pulled in. Equivalently, if the mass of the sun went to zero, the orbit would increase, okay? So this is just some effect that can happen there just because all of these baryons are falling in within the orbits of the dark matter particle. If that outcompensates the fact that you will have some outflow due to supernova, you can actually get an enhancement. So I found that very surprising, but this is just what they see in these simulations.
Sorry, I've been away from these, but is it correct to claim that this result, the orange line, shows that these guys are claiming baryon feedback solves core versus cost problem? There is no core versus cost problem?
So
is there a consensus on this?
So what? Yeah. So these. Okay,
Sorry, it's tangential. We can talk about it later.
I'll just know, but I just to say, somebody not in that community, that community is very good at conserving the number of problems. So what often happens is that they will solve one problem, but immediately introduce an additional problem. So I think that the core versus cusp is not what is the cutting. I think that we're not so worried about that anymore. This is one thing I would emphasize about that. The core versus cusp is often talked about in the context of dwarf galaxies, where the feedback you will get will be very different to the galactic center. What I think is now, and maybe I'm out of date on this, but the last time I looked at it, one of the problems they talked about for dwarfs was the diversity problem. And there they find a huge range from cusps to cores. And the question is, how do you get generically having that huge range here? But now again, this isn't a dwarf, but this already gives you some flavor about how baryons could give you that diversity because they can pull you in either direction. But I think to the experts, I don't think it's completely satisfied them yet at the level of the dwarfs, what's happening there. But I think that's the current version of cusp versus core. But yeah, we can chat more.
In the final to simulation, is the effect of the adiabatic contraction taken account as initial condition simulation?
No, good. So adiabatic contraction is just a basic property of gravity. So all that, they don't add this in. All that happens is the dark matter halo forms and the baryons slowly accrete onto the galaxy. And then as they cool down and form a disk and fall into the center, this is just a gravitational effect. So actually in a paper, in this paper here that I'll mention in a second by Abdelaziz Hussain and collaborators from 2025, they have an appendix where they just review how you can derive this adiabatic contraction. Essentially, the enclosed mass times the radius of the orbit you can prove is an invariant if the enclosed mass is moving slowly. It's just a property of gravity. So it's not something they have to add in. It's just some basic gravitational property.
As long as simulation start from the initial condition before collapse, that is automatically taken account.
Do you mean before the collapse of the baryons?
Baryon,
Yes, I believe that from the way that they often do these simulations, but I may be misspeaking somewhat here, is that they usually start them from essentially cosmological initial conditions, run them a bit, and then they find some ones that they want to study, and they do higher resolution simulations of these particular ones. But they really do start them very early on to get the right initial conditions. Yeah. Good. But this is just two different galaxies out of an n-body simulation. And if you wanted to go to a level of, say, you had some 95% confidence limit, you're not going to be able to do that off two realizations, okay? So, now, I mean, even then, the systematic uncertainties on these is not completely under control. There's a lot left to learn. However, as I said, it's not just Fire2 that is starting to do these simulations. There's actually a huge, I think there's four, of order 4 groups that are producing similar quality galaxies to this. And in this paper by Hussain et al. From earlier this year, what they did is they took the suite of all the Milky Way-like galaxies from all of these embodied simulations, took the ones, they selected on some features that they thought made them most Milky Way-like, and looked at what was the band of dark matter densities that you got out of this. And this is the band that they came up with. I think in total, though, they were using something like 20 to 30 simulations. So still not hundreds, right? These are very expensive simulations to do. But this is sort of the state of the art for the uncertainty band you would get. We think the density looks something like that here, okay? So it's still a lot left to be done here, but this is a huge improvement on just this 2 kiloparsec hardcore that we had previously. Nevertheless, what you want is you want to take this density profile, you want to shove it into this integral and evaluate. And that's what's called this J factor. And what is just a complete numerical fluke, I'm showing you the value of this J factor on the y-axis in some more fun units. And on the x-axis here, I'm showing you what happens to the inastro profile as I change the core radius. So going back here, initially I have no core and I'm just coring it at larger and larger radii so the J factor will go down. And by a complete numerical fluke, the lower end of the Hussain band is almost exactly 2 kiloparsecs, whereas where this Thelma one is at around 1.5, for example. So this is just to say that this thing that people have been doing in the literature for a long time for no good reason just turned out to be roughly where we are at the moment in terms of the lower band on the uncertainty here. One other point I would mention, though, in terms of looking forward, I said that there were 4 different simulation suites. It turns out that the lower end of this distribution is almost exclusively populated by fire. The other 3 all live up here. Now, ultimately, this probably shouldn't be determined by a majority vote, but some of the experts I've spoken to suspect that there are reasons that fire may be overdoing their feedback. And if that's the case, then maybe you would, in the coming years, as n-body improves, there's a chance that actually you'll move up to the higher end of this. But of course, it could turn out that the 5 people are right and the other 3 are making mistakes. We'll see. Good. So just to summarize this J factor part of the story, this is where the real, where the bodies are buried. This is a very challenging thing to estimate. And it seems almost impossible to infer this using observations, certainly not in the next 10 years. It's a very, very challenging region to map out because baryons completely dominate the inner galaxy. So even if you can measure the gravitational potential exactly, to know the dark matter, you have to subtract off all the baryons from this. Nevertheless, with n-body simulations, we're starting to get a sense for what is a robust lower bound on this. And I'm optimistic. 10 years ago, they didn't have baryons in these n-body simulations. In 10 more years, I think we'll know a lot more about this than what I'm showing you here. But it's easy to be optimistic about it when it's somebody else doing the work. Okay, so that's putting this all together then. What I've told you is that we can essentially get a robust lower bound on what would be the predicted flux from this. But also you should keep in the back of your mind, if you really have a hope that we're going to see a signal here, then you might be even more optimistic than you would have been with the inasto profile, because there's actually a chance for an enhanced annihilation flux beyond this. So one thing just to mention, in case you haven't thought about it before, is how would you actually detect a TeV photon? So this is the energy range we're looking at. Remember, these dark matter candidates are all up in the TeV window. So famously, the Earth has various bands through which the electromagnetic spectrum can pass through the atmosphere. TV is not one of those bands. So what are you going to do? Naively, you'd have to put something in space. Famously, that's very expensive. But it actually turns out there's a beautiful way of resolving this problem. You use the fact that the photons don't get through the atmosphere to your advantage. You actually use the atmosphere as a calorimeter. So what happens is the photon comes and hits the atmosphere, initiates a shower of particles. That shower will include charged particles. As those charged particles move through the atmosphere, they radiate Cherenkov radiation, and you can just compute that the peak of the Cherenkov radiation is actually in the optical. So by pointing an optical telescope, you can see this shower, reconstruct it, and you can actually determine there was an initial TeV photon. So this is a very, very old idea, but I think it's very beautiful. You turn the fact that the photon doesn't move through the atmosphere to your advantage. This is how instruments like HESS or CTAO operate. You actually also, you could just put vats of water high up in the tall mountains, and then some of the charged particles in that shower will move through the vats of water, and then they'll Cherenkov radiate in the water, and that's another way of detecting these, which is what Hawk or LASO does, for example, but I won't talk more about them today. Okay, so let me just tell you what the experimental landscape looks like briefly. So what I'm showing you here is the instrumental sensitivity, measured in some units I'll mention in a second, as a function of photon energy. And again, for the candidates we care about, we're really interested in the TeV range. So what I'm showing you on the y-axis here is what is the collection area of these telescopes multiplied by how long they run. And so this is an indirect detection analog of integrated luminosity for a collider. The larger this number for a given predicted flux from dark matter or pulsars or whatever you're trying to search for, you'll just see more photons. Now, of course, there's other ways to compare instruments. Some of them will reconstruct photons with larger or smaller uncertainties, have different backgrounds, but at 0th order, this is a nice way of comparing instruments. So you can see at lower energies, you have to go to space because the photons that hit the atmosphere create such a weak shower that you can't detect it. And we can only put things about 1 meter squared in space, and so we get limited. So this is what Fermi has been able to achieve. It's been a revolutionary instrument at the GeV scale, but it is somewhat limited just by the fact we have to put something in space. By the time you get to TeV energies, you can have something on the surface of the Earth, and now the instrumental size can increase dramatically. And this is what HESS, for example, has been able to achieve in this parameter space. I won't spend a lot of detail on this. I've already given Keisuke the rundown. But just to say, this HESS results need to be interpreted with enormous caution. Actually, the most recent HESS paper, I'm pretty confident, overstated their sensitivity by a factor of 8. I'll say one word about why that is on the next slide. But even if you take HESS and subtract that factor of 8, in some work I did with Ben Safdie and Linda Xu last year, we showed that the thermal WINO already seems to be excluded, even if you're maximally conservative about how what the dark matter density is in the galactic center. So maybe there's still a little bit of wiggle room here, but the WINO seems to be really under pressure. It probably isn't the dark matter of our universe, it seems. Nevertheless, there were some words I said in there, like we're using some data we think has a massive error and we corrected that error. You might be nervous about that. Just to quickly flash this, none of the HESS data is public, but they, in one paper, they gave enough information in their appendix that we were able to approximate their instrument response. And then once we do this, we can essentially redo their analysis. Just to tell you that we think we're roughly right, here is their published analysis in sensitivity in black, and here is our reconstruction of that in orange. So something seems roughly aligned, whereas what we think they should have reported was in red. It's about a factor of 8. And the reason we think that is that once we have their instrument response, we can say, what should they see if they look at different parts of the sky? We said, what should they see if they look at the galactic center in TeV energies? In the galactic center, we've got amazing measurements of TeV energies from Fermi. So you can just run the Fermi sky through the HESS instrument response and see what they should see. They should have seen this, and they claim to see counts down here, which to us tells us that they've got their instrument response wrong by a factor of 8. If you actually reduce this down by a factor of 8, you get a very good fit to the data. So it seems like they've just overestimated how good they are at converting flux into photons. Anyway, 100 emails later, they still disagree with us, but I have not seen anything in those 100 emails to convince me that they probably don't have an error. But to be honest, this is something we had to reconstruct from the exterior of what they did. They have access to all of the internal pipeline, but they're still checking it because they don't have a robust counter argument to what we've put forward here. So I think that their existing limits are probably overstated by a factor. Okay, but let's move forward. And moving forward, the instrument that will be a huge improvement on HESS is this telescope I told you about at the start, which is the Trenkov Telescope Array Observatory. So for those of you who haven't heard about it before, CTAO is going to be 2 sets of different telescopes. There'll be a suite of telescopes on La Palma, which is in the Northern Hemisphere. It's an island just off the west coast of Africa. And actually, this is where the first telescope I showed you was already constructed. This one I showed you at the start of the talk is on La Palma. So that's already operating, and they hope to have 4 of those large telescopes I showed you fully operating next year. And then they'll add another suite of telescopes to this that should become fully operational in 2028. The other site for CTAO is in the Southern Hemisphere in Chile. They've had a number of challenges in terms of getting this operating, but they're now very optimistic the optimism comes from the fact that they've secured the funding, that they will have this under construction soon and fully operational in about 2031. So still maybe 5 or 6 years away, but not that far off. So in terms of doing this search for just, I guess you're at the age where you have to do something with ChatGPT. Here's just in terms of searching for dark matter in the galactic center, it's normally taken as law that the only way of doing this is using the site at the Southern Hemisphere. And the reason for this is that if you're in the Southern Hemisphere, when you look up, you see the galactic center, okay? And these telescopes are designed to essentially operate by pointing straight up at the sky to reconstruct these showers that come down. In principle, the La Palma site can see it, but it would see the galactic center like the sunset. It's right on the edge of the horizon. It's not how these instruments were designed, so people normally say you're not able to do anything with that. So we'll come back to this, but let's just focus for a moment on what you could do with the southern side. Okay, so the essential takeaway, I'll walk you through this plot, but the essential takeaway is that using 5 years of data from the southern site, so this is the data we would have in about 10 years, in 2036, you can essentially test all of these real representations that I mentioned to you earlier on. So how are we categorizing this? On the x-axis, I'm showing you the representation from the WINO all the way up to this 13-plet. On the y-axis, I'm showing you the constraint we can set parameterized in terms of how large a core size would I need for this model not to be excluded. And by the time I've got to a core size bigger than 2 kiloparsecs, I'm saying it's excluded at that stage. So why do I have these bands? The central point corresponds to the central mass prediction, but the bands come from scanning across the full mass range and finding the weakest and strongest limit I get across that mass range. So remember the 13-plet had that enormous uncertainty on its mass. This is why we now get a large uncertainty band here. You can see that there's maybe a little bit of the 13 survives, but I think there's various tricks that I've talked with the experimental collaboration that you could boost this up. So I'm pretty confident that CTAO could reach all of these. And so this would mean that if it sees nothing, you could rule them out as being the dark matter of the universe, these very simple models. But on the flip side of it, it tells you if you fail to rule them out, you'll start to see a signal. Okay? The other aspect is another model that you can think about that I think is very interesting is the thermal higgsino, which is at about 1 TeV. And what I'm showing you here is what would be the discovery reach if we assume the thermal higgsino is the dark matter of our universe as a function of calendar year. I think this is a very visceral plot, because you can see where you might be in your life at various. So here is when CTAO south would turn on. And you can see if you're in this adiabatic contraction, this optimistic scenario, you would find that almost instantly after turning on, you would have months. You would have a 5 sigma discovery, which is reasonably optimistic. Whereas if you're in this inasto profile, you'd start to see a signal relatively quickly, but to really reach 5 sigma, it might take a number of years. If you have strong baryonic feedback, the situation becomes more pessimistic. But to remind you, for the higgsino, the only other game in town I'm aware of is a 100 TeV collider, and that's quite a way off on the right-hand side. So the other aspect of this that we dug into in a paper from earlier this year with 3 members of the CTAO collaboration was, could you do anything with the northern telescope? Because let's say you're impatient and you don't want to wait for 2031. It turns out that, and there's been demonstrations now showing that this works, that yes, it's not the way the instrument was designed, but it absolutely will operate if you point it at the horizon. So there's various aspects of this, essentially because you're looking much further away, your reconstruction of the energy and the angle the photon came in will be worse. And also you lose sensitivity to lower energy photons because the shower has to travel further and it gets diminished by the time it reaches your instrument. But it turns out the instrument still operates very well. And so the northern sight, once it has these 4 telescopes operating, again, if you're in this optimistic scenario, we could have a discovery of the higgsino at 5 sigma within a couple of years, which I think is it's something I'm very excited about.
The line search or continuum search?
Here we're using the line and the continuum, but it's almost completely dominated by the line because the continuum is somewhat degenerate with the background. If you just had the continuum, it would reduce a bit, it would reduce noticeably, but the line is really critical. And so these are just 2 examples of what you could do with this instrument. There are many others. Let me just flash a few instances of what you would be able to do. And maybe just to give you the heart of the aspect of the reason why so many models should be testable with CTAO, that is because this will be the first instrument that can really probe thermal Rayleigh cross sections at the TeV scale. And so if you believe that this WIMP miracle, and you think that the same annihilations that set the Rayleigh abundance are happening today, and your dark matter is at a TeV, if you are able to hide it from direct and detection and colliders, as you have in these minimal models, this would be the first instrument to see a signal. So I'm just showing you here, like this is sort of the generic sensitivity for some annihilation into WW. You can see that you could have, for the ionosphere profile, you have sensitivity up above 10 TeV to this thermal Rayleigh cross section. But of course, then you can think about more UV motivated models. There's an example, for example, that I'm working on with an amazing group of people at Maryland, showing if you revisit these old ideas where you have dark matter from extra dimensions, the way that these are realized is also often as a TeV scale WIMP. And there is sort of a funnel region of parameter space that is excluded direct detection, but indirect detection will get there. And then there's a beautiful example from the local group that Keisuke asked me to make very large. And so I'm told that for some of this is a model of where you have these some parity partner to the Higgs that makes up the dark matter. And in these scenarios also, I'm told that CTA would be able to have a very good chance at either seeing something or excluding them if it's unable to. But I think this is just a taste of the many models that you might be able to see here, and only adds to my excitement that a discovery could be in the near future. Okay, with that, let me just wrap up with that main image. Like, I know there's been a lot of null searches on the road along the path to detecting dark matter, but I have a lot of optimism that this might be the instrument that finally gives us a chance of changing that. Okay, let me leave it there. Thanks for your attention.
If we see a signal, we have seen signal. Every time we see a signal, somebody invent a background.
Sure.
Could this be any conceivable background that we can think of for this kind of signal?
Good. So if you see a signal of the variety that is like these sort of continuum searches, like here, which both of these models, I believe, are essentially giving you a continuum, it will be hard because we would really need to understand the smooth background very accurately to be confident.
Because the line is very suppressed.
In some of these scenarios, if you don't have Sommerfeld, the line is down by a loop factor, and so then it's generically irrelevant. Yeah, you need the Sommerfeld to essentially undo the loop factor, because now you have a chance of ending up in pi plus chi minus. So I think in these model you also don't have Sommerfeld. Is that right?
No.
Yeah. So then I think here you also don't have a line. So you're generally looking for the continuum annihilation.
Yeah.
Now I think at that stage you probably need to see this in some other object to really convince the community. It'd be tough, right? And again, it'll be the galactic center excess all over again, probably. But I mean, that's a good, that could be how dark matter is.
Mm-hmm.
In the case of these models like the minimal dark matter, though, where you have the Sommerfeld annihilation, you get this line, and it is, look, if such a thing is announced, there will be papers showing how astrophysics can give us TeV line. But to give you an example of this, you might remember the story of the 130 GeV line.
Yeah. And
I'm actually only aware of one astrophysical model that was put forward to that, and it's deeply contrived. Like, the challenge is that usually you need to do this with cosmic rays at these sorts of energies, and most cosmic ray spectra are power laws. How do you need some very cold, like narrow distribution to do this, and people had to turn every knob to 11 in order to get something that they thought could explain the 130 GeV excess. And it was clear that as you go to higher and higher energies, it becomes harder and harder. Now, of course, we will have to cross-check this carefully, and it would be a great reason to build the 100 TeV collider if you saw a higgsino signal, for example, to really cross-check this. But in the line case, I'd be more optimistic that we could become convinced of this than in the continuum. That's a good question. Nico, did you have a question on that?
Yeah, it was similar to like, but it was about like you have these two telescopes, right? One like looking like that, the other one looking like this. So when you did like your like modeling of this is like I will get like this a lot of like on like systematic.
For sure.
So
Yeah,
like how like do you model this like how you model this?
We put in some treatment of the systematics, but of course it's always somewhat naive before the instrument's even turned on.
Okay.
So what we are doing at the moment is working, because I said one of the telescopes is actually operational. We're putting in a proposal to use some of their early data to test some of our ideas about how the systematics operate. So I hope that we could refine these estimates with real data in the coming years. But yeah, it could be that the case is a factor of a few worse than what I'm showing here. You still have a lot of discovery reach, but we'll have to wait and see. But this is something we're worried about, but you have to wait till you have the actual telescope to know. Yeah. Please.
Is it an issue if you miss significant fractions of the shower because it spreads out so much, or is it so high energy that it's very highly directional and you basically collect the whole thing?
No, that's a really good question that goes into how this operates. It's roughly a function of photon, incident photon energy. As you go to higher and higher energies, the showers become larger and larger. And so actually, I didn't go through this here, but what CTA will be, it'll be an array of different size telescopes. So the one I showed you are the largest telescopes, and they are best for looking for the lowest energy photons. And there the shower is not so large, but it's very dim. So you need like a very large collection area of your optical telescope. Then going to the other extreme, the medium you can interpolate. But then the other one, you have many spread out small telescopes. Because there the shower is very bright, but very large. So you do this to try and capture it. But eventually, what will happen is that as you go to high energies, you're uncertain, you'll still see something happen. It'll light up all of your detectors, but you'll be very uncertain about what the energy was. Like many of your reconstruction statements will be way off. And of course, like I'm showing you, CTA, I think they claim they'll be able to measure photon energies robustly up to 300 TeV actually, or maybe even 500, I'm told. But we know of particles at much higher energies, right? So for example, Pierre Auger has seen states up to 10 to the 21, so 10 to the 12 GeV. And those, the way that they collect that is by using these sort of water tanks spread over square kilometers. This is like you have to, because the shower is so large now, to reconstruct, you just have to make it bigger. So the fact that these things aren't enormously spread means that they'll lose sensitivity at some point, but that's okay. It's still very good for what we're looking at.
And when they say robust up to 300 TeV, what's robust numerically, like percent level precision, better than that?
So what, so if I go back, so in terms of what they'll actually be able to achieve in terms of all the systematics, I don't know the numbers off the top of my head. I know the references to look up, but you can maybe just to relate it to what you were saying here. A lot of these, you see that they just cut at some point, and you ask why are they doing that? The reason is that even in the dark matter case, essentially every spectrum of photons you get in the universe falls as roughly e to the -2. So as you go to higher and higher energies, there's just fewer and fewer photons. And at some point, how do they get these? They run Monte Carlo simulations of their detector from end to end to determine what the instrument response is. And at some point, they think that the odds of seeing a photon at these energies is so pathetic that they just don't bother running simulations. So you can see it's starting to degrade, but then Hess doesn't think they'll ever see a photon up here, so they just don't run the instrument response. So there will be some degradation up here, but the hard cut actually comes from, that's roughly where you don't expect to see a photon anymore. And then, but in the case of dark matter, you can motivate that there's a chance that there could be a higher, like astrophysics, but dark matter can give a boost on top of that. So this is why talking to some internal people, they think that they might be able to push their reconstruction of the instrument response up to 300 or 500 TeV. But if you look at anything public, they normally actually often stop at around 100 TeV. Here it's gone up to 180 or something like this. But Yeah, anyway, those are some words towards what you said, but not a rigorous answer. I can give you some more offline if you're interested. Thanks.
I can ask a question, might be a little further outside your wheelhouse, but I'm just trying to understand why the best way to map the core of the Milky Way is to go through this convoluted path, like through observations, through simulations, like back to and making all that uncertainty, as opposed to, you know, what kind of dynamics measurements we can get and just measure directly, and like what radius can we push down to before we have to just start extrapolating a model of that sort.
Yeah, no, it's a very reasonable question, but the heart of it is the baryons, as you get towards the galactic center, are more than an order of magnitude larger in terms of the total mass than the dark matter is. So you're trying to infer some small fraction of the total, the distribution of some small fraction of the total matter that you can't see. And so to do this at minimum, you need a complete accounting of all of the stuff that's in the galactic center. It's very hard to see because other stuff obstructs, a lot of it will be gas. And there's a lot of the other stuff there will block all of the light coming out of this that we would want to see. So it's just hard to get a full accounting of what is there. And then secondly, to get accurate probes of the potential all throughout the inner few kiloparsecs is just very challenging. Like Gaia has been an enormous leap forward, but it becomes quite incomplete as you get towards the galactic center. So there's a lot of gaps we have in our knowledge there. So the people I know, people are pushing towards that, but this is a problem that will not be resolved on 10-year scales, an actual measurement of this. It's not to say it's impossible, I think in the direction you were saying, but on the 10-year time scale, I'm much more optimistic that we will learn about this through simulations. And that's the reason I focus on it. I would wish we could do the direct thing, it's just much harder.
Another follow-up on that, I guess, is like, when I hear people quote the total mass of the Milky Way, it's still generally uncertain by like a factor of 2.
Yeah.
Does that factor of 2 normalization like still affect, you know, these bands that we're putting on, or was that like incorporated in that same?
So there's another, not so much, because I think that okay, so here's the reason for this statement. The dominant contribution of the mass to the Milky Way is dark matter. But within the solar radius, dark matter is completely subdominant to baryons. So really, getting the total mass is getting the distribution out at much larger radii, which is sort of orthogonal to what we're doing here. Nevertheless, there is another factor of 2 that I swept under the rug, but that's fine, because there's another thing that is even more concerning, and that is the fact that you might notice here, I've pinned all the profiles at our Earth radius to be exactly the same, but we're uncertain about, and I just pinned them to some value for the local dark matter density. I think I took 0.4. But we think that the dark matter density could be between 0.3 and 0.6, and there's systematics on that as well. So that's somewhat related because some of these measurements use more global observables to try and infer what the local dark matter density is. But you can also wiggle this thing up and down by a factor of 2, I would think as well, although I took towards the lower end of the current accepted band for this value here. But that factor of 2 is still smaller than the value we get from this extrapolation inwards.
So you're not optimistic at the action people.
Huh?
You're not as optimistic as the action people.
Well, let me not get into that. They often take a value of like 0.65, which I think is ridiculous.
Maybe you just got lucky.
Optimistic.
They have a local income.
The problem with that though is that if in 10 years this band turns out to be the real one, they won't have hit the DFSZ at all. Right, so anyway, that is a bit disappointing, and they're not going to go back. So I wish they would be a bit more conservative.
Can I ask you something? It's more like me thinking out loud, just like also like people you're just yeah. So there's another handle to kind of like, if you discover this could be another handle. I don't know, like if you have like, I don't know, like some like pump, and then you can heat up, I don't know, like the AGM, like or like an alpha, like because you're gonna have to put some heat. If you so like I don't know, like have you thought about those?
The energy injected is pathetic. Yeah, it's just very, very small. Like a tiny fraction of the dark matter is ever in its in the history of the universe annihilating to these processes. It's just there's not a lot of TV photons in the universe, so you have a chance of seeing this. But the total energy is
So you don't have like this patchy radiation that you, okay, I could.
Yeah, no, I don't, it's just you generally need much lower mass dark matter to have, to do this. Also at some energy this changes, but a lot of very high energy photons will just run for a long time without ever interacting with anything, so they're not going to heat anything up. But if you saw something, the next best chance that we have is just to do the same thing with a dwarf or something like this. And the hope is that with instruments like LSST or Spec S5 that people are talking about, you might find a better dwarf than we have. Because at the moment, the best dwarf is more than an order of magnitude below the low end of this band in terms of the J factor. So it'll be very hard. So we hope we can.
So suppose CTAO finds some possible signal. Can it follow up by, for example, let's see, the positron surge or anti-helium surge? Or
That's a fair point. No, yeah, you will eventually expect a signal in other channels. Again, though, you just need some obscene sensitivity at TeV. So I don't think AMSO2 is sensitive to a thermal relic cross section at TeV. Nothing else is. Like IceCube isn't. But eventually that would be a prediction. At these energies, you can't just go into one state. You have to go into all the others. So you would have a robust prediction for maybe putting another antimatter spectrometer on the space station or something like that. I haven't thought about the numbers off the top of my head. Also, maybe a sociological aspect of this. I don't know if you would convince the community by seeing something in cosmic rays, right? It's so messy.
It's actually positrons.
Yeah, they've been burned too many times. I don't think antiprotons would be better. And also, even the flux you get of anti-helium-3 is anyway. I don't. That's complicated. Right? People debate that a lot.
There are no more questions. Let's thank you again.